Okay, let's do a quick practice. So one way you could do this is to just label which side of this is south, which side of this is north, and then figure out if it's going to attract or repel. Instead, which again would be the simple way to do it, instead let's think about the magnetic field caused by this bar magnet and use that magnetic field to understand the forces here. So our bar magnet, you're going to get a strong field that comes out here and loops around. So it's coming out from the north into the south. And I'm not very good at drawing field lines. So I haven't done a great job of symmetry, but we're going to have to kind of go with that. So again, when I draw the field lines this way, I have to think about what is it really going to look like at these points. So again, at the top we have current in, at the bottom we have current out. My magnetic field at this point, due to the bar magnet, it looks like is going to go something like that. My magnetic field at the bottom looks like it's going to go something like that. So at that point, we can say, okay, that's my magnetic field vector. What is my force going to be? Well, at the top, we have I cross B. I cross B is going to give me, now, and this is actually a harder version of the right-hand rule because you have to keep in mind that whatever force we get is actually perpendicular. So the force up here is actually something like this. So we have a current that's in, magnetic field down, we get a force that way. At the bottom, I cross B is going to give us a force up. So now that's going to give me a net force that is pushing away, which means that it's repelled. So let's double check this. I just said doing this the hard way that it was repelled. Let's do it the easy way. So the easy way, I look at this. Now, one of the things you can do is just use the right-hand rule directly to say that my magnetic field on the inside, which we know looks something like that, is actually going this way, right? And you can do circles if you prefer. But so we see that this is what the magnetic field from the loop looks like. And going in is south, going out is north, south and south, repel. So obviously this is the easier way, which is why we like talking about poles. Talking about north and south poles is a much faster way to deal with things. So if you can do that, please do. But keep in mind that south and north poles are only defined for things like loops, that if you have a wire, a long straight wire, you can't talk about the south and north pole from it. So think about south and north poles if you have two dipoles, which is a loop or a little bar magnet, or even a solenoid. But otherwise, you're going to have to explicitly use current to magnetic field to find your force. So one thing that I want to point out, we just did a version of this where I labeled what the magnetic fields were. Note that in this case, we have a different orientation. We have a north pole. That we do get a net force. This is actually going to be a homework problem that you're going to do because this is really interesting to think through and calculate that value. However, there's something to be careful about. This is a non-uniform magnetic field, right? That this little dipole does not create a uniform magnetic field. The only object that creates a uniform magnetic field is when you're inside a solenoid. So you don't have a uniform field here, so you do get a net force. But you're not going to have a net force on your little current loop in every situation. You only get it in this non-uniform situation. So let's think about a uniform field. So this is a modification of a figure from the book. It might not be very clear. But now we have a uniform field, right? Notice that we have this uniform field here. And so we have a loop. Now this is a square loop. Don't worry too much about that. And it's oriented at a slight angle from our magnetic field. That's also not very important. What we want to do is think about the magnetic force on each piece of the loop. And this is pretty easy to do with a square rather than a circle. So in this case, we think about just the top portion. And when you do I, which is this way, cross B, you get a force that's up. But now when you do I cross B on the bottom, notice that your I is going the other way, but your B is still the same, you get a bottom force that is equal and opposite. Same thing happens on the side. So you have 4 forces, but when you sum up your forces, you get 0. The directions cancel on top and bottom, strengths are the same. Directions cancel, front and back, strengths are the same. So if you put a loop in a uniform field, you have no net force. So again, you do get a net force if it's a non-uniform field, but there's no net force if it is a uniform field. And that just has to do with whether or not the direction is the same at every point on the loop or not. So please be careful about this. Don't remember one of these two situations and apply it to everything.